Hello guys, Dr. Hasbullah here, and in this video we're going to be looking at impulse turbine. In the previous lesson, I've mentioned to you that there are two types of turbine classification, which is the reaction turbine and also impulse turbine. We've covered reaction turbine before, and now it's time to cover the impulse turbine. For me, I think the impulse turbine is a much simpler device as compared to the reaction turbine. For reaction turbine, one type of reaction turbine is called Francis turbine. And for impulse turbine, one device that is an impulse turbine is called the Pelton wheel. And it looks something like this. So Pelton wheel is basically a very big wheel with a few buckets around it. Okay, so you have buckets here. And to move the wheel, you have a jet, right? And this jet is going to inject water into this wheel, right? So this is the water. And this jet is connected to water reservoir somewhere. And the water goes here and into the bucket. And this spins the entire Pelton wheel. And a Pelton wheel can have multiple jets or multiple nozzles. Okay, this is called jets or nozzle, right? And this is called the Pelton wheel, and this is called the bucket. In case of multiple nozzles, let's say it's got two nozzles, so this might be another nozzle, right? That's also going to inject water into the wheel. If you notice, now it is quite clear the difference between a reaction turbine and also impulse turbine. So for reaction turbine, you have everything inside a container, right? You have everything inside the volume, right? So inside the volume, you still have the pressure and also you have the kinetic energy. But for this type of turbine, the impulse turbine, so all the potential energy here is converted into kinetic energy, right? So when the water hits the turbine, it's all kinetic energy. This is impulse turbine. For reaction turbine, the water that hits the blade has kinetic energy and it also has some pressure. For this type of turbine, the Pelton wheel, there is no more pressure. Pressure is ambient pressure, but what it has is the kinetic energy because the jet is simply exposed to the atmosphere. Now let's dive a little deeper and take a look at the equations, right? Let's say I want to take this bucket, right, and I want to analyze it and to create an equation for power, efficiency and everything. So if I draw it again, but this time I want to draw it from the top, okay, and this is the side view, but I want to draw it from the top. Usually it looks something like this. Okay, that is how usually your bucket looks like. So this is bucket. And the water jet comes from the left. Okay, here is the water jet. This is the nozzle. Remember that for Francis turbine, you have velocity triangle. But this is much more simpler, right? You don't even have a triangle. Okay, now what does the velocity component looks like for the Pelton wheel, right? So first of all, you have the velocity of the bucket. That is u, right? So this bucket has velocity, which is u. And u is equal to omega r. What is our omega? Our omega is the rotational speed of the Pelton wheel, and our radius is the radius of the bucket to the center of rotation, which is r. Okay, and u equal to omega r. Okay, so u is the velocity of the bucket. Okay, what else do we have? We also have the velocity of the water jet. Okay, and this is called V1, capital V1. Okay, this is the velocity of the water jet. When we have U and we have V1, we also have another component which is called the small v1. Okay, and this is equal to capital V1 minus U. U is the blade speed. Okay, let me write it here in orange. So this is blade speed. Okay, and V is the jet speed or the water jet speed, okay, and small v is the relative velocity. Now, this is what I meant when I said that the impulse turbine is much simpler than a reaction turbine, because we don't have any alpha, we don't have any beta, everything is moving in a straight line. So to get relative velocity is just V1 minus U. It's that simple. So what happens when the water hit the bucket? Right? What happens is that the water will turn and it's going to exit at that side. And now we have a little bit of an angle so that the water can move out without hitting the water coming in. Right? You cannot have the water go and then go back at 180 degrees, because then it would hit the incoming water, so it won't be very efficient. So it has to go in and then deflected a little bit so that it doesn't clash with the incoming water, right? And this angle, let me draw it here. So this will be your small v2, right? So 2 is exit, okay, and small v2 is the relative velocity at exit. U is still to the right hand side, okay, because the bucket is still moving to the right. So this is your U. And when we have U and we have V2, so what's left is just capital V2, right? And we have an angle here that is called the beta 2. And beta 2 is called the deflection angle. And this deflection angle usually varies between 160 degrees to 168 degrees. Okay, remember, it cannot be 180 degrees. Ideally, we want it to be 180, but we just cannot. Now, how do we find torque from this figure, right? And before we find torque, we need to find the force. And if I do the linear momentum equation for force is m dot v1 minus v2. Right, so m dot is rho times q, and v1 is the velocity that hits the bucket. In our case here, the velocity has to be the velocity that the bucket feels. Right, now even though our jet velocity is capital V1, but when we have a jet, right, and we also have the bucket that's moving away from the jet, isn't it? Okay, so the bucket will not feel this velocity, but the bucket will feel this velocity minus the velocity that this is moving. So the velocity that the bucket will feel is actually this velocity, the relative velocity, and that is very important. Okay, so I'm going to replace this with small v1 minus small v2. Right, and if I want my force in x direction, okay, so summation of force in x direction, so that's going to be rho q V1 minus V2. Okay, now V1 is quite clear, it is in x direction, but V2 we have a little bit of an angle. So I'm just going to do rho Q V1 minus V2 cos beta 2, right? And that gives me the V2 in x direction. Okay, but now one important assumption that we need to make is that the blade has no friction. Okay, and that means when the blade has no friction, so no friction, that means V1 equal to V2. Okay, and if I replace it here, so that's going to be rho Q V1 1 minus cos beta. Okay, does that make sense? Simply replace V2 with V1 because our assumption is that the blade has no friction. So this applies. Okay. Now that you have the force in x direction, how do we convert force into torque? Right? So torque is simply force multiplied by radius. And where is this radius? And this radius is here. Okay, that is the radius. So what we have now is rho Q R V1 1 minus cos beta 2. Right? And if I want to write it more clearly here, so torque is going to be rho Q R. And what is our V1? Okay, our V1 is this term. Okay, V1 equal to capital V1 minus U. So this is going to be capital V1 minus U, 1 minus cos beta 2. Now that you have the torque, and if I want to find power, I think you know how to do this. Power is simply torque times omega. And where is this omega? Omega is going to be here. That is your omega. Omega is the rotational speed of the whole wheel, right? Now, what's going to happen here? So you have rho Q omega R V1 minus U 1 minus cos beta 2. Okay, so omega times R is quite clear that omega times R is equal to U, right? So this is going to be rho Q U V1 minus U 1 minus cos beta 2. Right, and that is your final equation for power. And to make things clear, we're going to call this W dot T. This is the power generated at the turbine wheel. Okay, so this is rho Q U V1 minus U 1 minus cos beta 2. Okay, later you will find out that we have W dot T, which is power generated at the turbine wheel, and then we have W dot F, which is the power supplied by the fluid to the turbine. Okay, and then you can find efficiency from there, right? So you have U here, and you have the negative sign here. That means that this equation is a quadratic equation with a peak, right? It's going to look something like that. That means if I plot the graph of W dot T against U, I'm going to have a single peak, isn't it? Now, how do we find the peak velocity? You can find it by differentiating W dot T against U. So if I do this here, so if I do dW dot T over du equal to 0, this is where I can find U equal to U at maximum power. Right? And maximum power is very interesting because you always want the turbine to output the maximum power that it's designed for. Okay, so let's try and find this maximum power. First of all, I'm going to combine these equations. Okay, so this is going to be rho Q U V1 minus rho Q U square times 1 minus cos beta 2. This is equal to rho Q U V1 minus rho Q U V1 cos beta 2 minus rho Q U square plus rho Q U square cos beta 2. Right, now it's quite simple to get dW dot T over du. This is simply rho Q V1 minus rho Q V1 cos beta 2 minus 2 rho Q U plus 2 rho Q U cos beta 2. Now, if I factor this out, right, I'm going to have rho Q V1 1 minus cos beta 2 minus 2 rho Q U. This is 1 minus cos beta 2, and I can have rho Q V1 minus 2 rho Q U times 1 minus cos beta 2. Is that right? Okay. And if I equate this with 0, and I can have this equal to 0, so rho Q V1 equal to 2 rho Q U. And if I cancel this out, I can have 2U equal to V1, right? And I can have U equal to V1 over 2. Okay, and this is important. Okay, so whenever U is equal to half the jet velocity, you get the maximum power. Okay, so basically in here, in this figure, whenever this U is half of this velocity, you get the maximum power, right? And now you know that at this point, U is equal to V1 over 2, right? And how do we find this V1? Okay, and V1 is found using this equation. V1 equal to CV square root of 2G HT. And what is CV? Right? CV is called the velocity coefficient. And HT is the available turbine head. And the value for this velocity coefficient is usually between 0.98 to 0.92. And don't worry if you are not sure how to use this equation yet, because after this we're going to do a tutorial. Now that we have the turbine power, okay, if I draw this again, this is the turbine and this is the fluid. Okay, and at the turbine, the power is W dot T, and this is equal to omega dot T just now. Okay, so this is your final term for turbine power. Okay, and at the fluid, you will have W dot F. Okay, and W dot F is equal to rho GQ HT. And when the energy is transferred from fluid to the turbine, you will have efficiency, right? So this is called the turbine efficiency, and the turbine efficiency is defined as W dot T over W dot F. So this is going to be omega T over rho GQ HT, because the energy is being transferred many times. Okay, so from the fluid to the turbine, and let's say the turbine is going to transfer the power to the generator. Okay, so this is the generator. Okay, and then there is another efficiency here that is called the mechanical efficiency. So the turbine must be on a shaft, right? And this shaft must has bearing in order to hold it in place. So because of that, it will have friction, and that will reduce the power from the turbine to the generator. And the efficiency is called the mechanical efficiency, right? And let's say the generator, we're going to use W dot O, output power, right? And the total efficiency between the fluid to the generator is called the overall efficiency. Okay, and the overall efficiency, eta O, is the multiplication of eta turbine efficiency times the mechanical efficiency. Okay, now you have the overall efficiency, meaning that the efficiency from the fluid to the generator. So from fluid to the turbine, it is called the turbine efficiency, and from the turbine to the generator is called the mechanical efficiency, and the combination of these two efficiency is called the overall efficiency. So remember guys, you have a few types of efficiency and you must know exactly where and when to use it. And coming back to our turbine efficiency, which is eta T equal to W dot T over W dot F equal to omega torque over rho GQ HT. And if I want to use this equation, okay, and I want to combine this equation with this term, let me find it here, I mark it as purple. I want to combine it with this term, and also I want to combine it with this term. Okay, remember that you have V1 there, right? And I'm going to use this V1 and put it in that equation, right? And in that equation, coming back to this equation, I will end up with something that looks like this. This is now 2 phi times CV minus phi 1 minus cos beta 2. Sorry about that. This is cos beta 2. Okay, and this phi is a combination of parameters which are R times omega divided by square root of 2g ht. And the reason why this is combined together is because usually R and omega and also g and ht in an operational turbine will remain fixed. So now this is eta t, and I can now plot the relationship between eta t and also phi. And if I do just that, okay, you see that the relationship, this is eta t and this is phi. And if you plot that, you're going to have a graph that looks something like this. Well, I think you kind of expected that because this is a quadratic graph. And again, when you have a peak, okay, you want to know what is the phi that is going to give you the maximum efficiency. And this point happens at phi equal to CV over 2. So basically this is a completely different graph. This is efficiency against phi. And just now we plotted this graph, but this is turbine power against U. For this graph, the maximum power happens when U is equal to V1 over 2. Right? And for this graph, the maximum efficiency occur when phi equal to CV over 2. And the range of Pelton wheel efficiency is about 0.8 to 0.9. Okay, and what are the reasons of these inefficiencies? Okay, what are the reasons for these losses? For that, let's take a look at the bucket figure. Okay, and this is the figure. And let's take a look at this, right? So the reason for inefficiency, let me write it somewhere. So inefficiency, it could be that the jet does not hit the bucket at a uniform velocity. So first, non-uniform velocity. And the next reason of inefficiency is, if you remember, just now we assume that V1 equal to V2, right? We assume no friction whatsoever inside the bucket. But in real life, of course, there are friction in the bucket. So it could be friction in the bucket. And finally, that I can think of is the friction that is inside the jet. Okay, because inside the jet, you have the water and you have the converging section, right? To increase the velocity because you want the maximum kinetic energy, right? But in doing so, there might be some losses inside that nozzle. Okay, so this could be losses in nozzle. So those three are the main source of inefficiencies. Of course, there are many other sources of inefficiency, but those are just an example for you. So with that, I think that is all for impulse turbine. So please study this again and again. For me, this is much simpler than the reaction turbine because there is no velocity triangle involved. So you don't have to worry about drawing velocity triangle. But there are a few equations that a little bit different from the Francis turbine and also from the pump. Okay, so do this again and again until you understand what's happening here, and in the next video we're gonna do some tutorial. So for now, that's all from me. Thank you very much. I'll talk to you soon. Bye.